Okay, gravitational potential energy part 2. In the last video we established that when you move against the gravitational field, the gravitational potential energy of an object increases, and when you move in the direction of a gravitational field, the gravitational potential energy of an object decreases. And we decided decided to set the place where the gravitational potential energy was 0 as being at infinity. So today what we're going to try and do is we're going to try and come up with an equation, come up with a formula that will state what the gravitational potential energy is at a position in a side of gravitational field. So first thing we have to understand is that up here we've got no energy, down here we've got a negative amount of energy, and that it's given by the work done moving against the field. Now in this case, because we're not moving against the field, we're moving with the field, this work's going to be a negative value. So let's think about the forces acting. First thing to understand is that work is force times displacement. Now again, this is assuming that we are working against a force. Okay, so the force is a vector, the displacement's a vector. As long as the force is in one direction and the displacement's against that force, we've got positive work. But if these are in the same direction, we're going to have negative work done. We're not doing work for the system, it's doing work for us. So, with this in mind, let's think about what the force versus distance or separation graph will look like for an object let's say of little mass m. Call that, I'm not even going to draw a circle, I'll just call it m. It's an m-shaped object in a gravitational field as it moves from infinity to a position in the gravitational field. Well, the force that experiences is given, of course, by Newton's law of gravitation. F equals big G, which is a constant, times the mass of our planet, times by the mass of our object, divided by its separation squared. Now this, of course, if we were to plot a graph now of the force versus the separation, then we would find as this distance r increases and gets bigger and bigger and tends towards infinity, then the force of attraction between the two objects is going to tend towards 0, and that's grand because that makes things handy for us. Also though, we're going to find as this separation tends towards 0, this force is going to tend towards infinity. Now luckily for us, both the masses are not point masses, they're spherical objects with a radius, and so this will never get to infinity. Okay, it's going to stop somewhere. But what it would mean is that if we were to think out some distance out, let's drag this axis out a little bit further. Some distance out here, the force is 0 or near to 0, and as we come in, this force will start to get towards 0, start to get towards infinity as it gets super small. But we're not going to worry about this because this doesn't actually happen. This bit of the graph doesn't actually exist because we can't get the masses any closer together than we'll call R0, and R0 of course is the radius of our big mass M. Assuming this is a point mass, let's say this is the R0 is our big mass M. But theoretically, if it was a point mass, they could go to an infinitely high force. So we want to work out what the work done is in moving an object from infinity to some point in the field. Let's say we're going to bring it to R0. And of course what that's going to mean is it's the area under this graph. So basically it's the work done. The work done, of course, is the area under this graph here. This bit here. So how do we find out the area under a curved line? Well, it's a bit of a pain. You don't really need to know the proof for A-level physics, but the only way you can really explain it is with a bit of calculus, a bit of integration. So if you have to, first of all, you have to consider a teeny weeny slither, like a little wincy slither of this graph. The idea of making it a wincy little slither is that at the top there's no difference between this side and this side of the slither in terms of the force. Okay, so we can explain this slither. Let's say the area of this slither, okay, will be the work done because it's a tiny bit of area. So we'll call this dr, delta r, and we will say that the work, the W is equal to the force times dr, that's the area for that little slither. And of course the work done under the whole graph is going to be the sum of all these tiny little slithers. We add all the little slithers up, we're going to work out what that value is. And so in order to do that, we're going to need to do a bit of differentiation, sorry, not differentiation, integration of course. Okie dokie, so here's what we're going to say. We'll say the potential energy, EP, is the sum of all the tiny slithers between the values of infinity, going from infinity to R0, of the force with respect to R. Now, are we going with a force, so it's ID, sorry, against the force, i.e. this is positive? Are we going with a force, i.e. this is negative? Well, the answer is, of course, we're going with a force. I'm going to put in that minus sign right here. And again, this harps back to that last video. That's a bit counterintuitive, but this is a vector and this is a vector, and we're going in opposite directions. So, now we've established this. What we want to do is we want to basically put the force in terms of Newton's gravitational equation. So, we will say EP is equal to minus big G, big M, little m over R squared, and we're going to integrate from infinity to R0 with respect to R. Oops. Okay, once we're doing that, we can say, well, this is a constant, this is a constant, this is a constant. Well, this is the only thing that's varying as we change. So we will say we're going to integrate from infinity to R0, and it's going to be equal to, we're going to take all the constants outside. So minus G M M. Oops. Leave that there. Minus G M M. Give me 1 second. I'll sort out my PowerPoint. I'm not that flash. It's going to be minus G M M times, I'm going to integrate R, which is now R. Oops. R to the minus 2. So that was R squared. That should be R squared there. So this is basically constants on the outside. I'm going to integrate R to the minus 2 between infinity and R0. Now what this equates to, what this basically gives us, if we integrate R to the minus 2, we get minus R to the minus 1. And we get, move that over a bit, we get minus GMM times by minus R minus 1 between the values of R0 and infinity. So what this basically tells us, what this basically means is that if we said all of the red area, okay, we want to work out what is the red area there, we would have to say, well, it is all of the area under the line all the way back to nothing minus the area from nothing to there. So the red would be the total area under the graph, assuming we can go all the way to infinity there, minus this green bit here. And this, with that in mind, what we'll do is we'll start to make a bit more sense, hopefully. We can say the potential energy, the EP, is equal to, I'll put this all back together now, it's going to be minus GMM times by minus R to the minus 1. So that's going to be minus GMM. Now the minus and the minus cancel out, so I'll get rid of that. And our first value is at infinity. Okay, so R's on the bottom, but that's infinity. Minus, I'll put that in little square brackets, minus GMM over R0. Okay, I should really put R0 in there, but that's R0. Okay, so minus times minus, this is a minus, this is a minus, these become a plus, and it's minus these two, which are both minuses. So basically these two minuses cancel out, and we can say that because this lot's divided by infinity is nothing, the potential energy at R0 is going to be equal to minus GMM over R0. And And that is basically it. That's the potential. Oops, I didn't put the minus sign in. That is the potential energy equation. So for potential energy of any object in a gravitational field is equal to the universal gravitational constant times by the mass of the big object times by the mass of your little object that you're looking at, divided by the separation between the two. And it's a negative value every single time. Okay, and that is the equation for the gravitational potential energy. Of course, if we want to now think about what gravitational potential is, okay, if we want to think about the gravitational potential, well, V, the gravitational potential, is of course the potential energy, EP, over unit mass. So basically we just take out the m there, and of course that will now be minus gm over r. And that is it. And that is all there is to it. So there you have it. First things first, the gravitational potential energy is a negative value wherever you are in the universe. So it is minus gm, big M, little m over r. And the gravitational potential, which of course is the gravitational potential energy per unit mass, is minus gm over r. And with that in mind, you can go off and do some maths about this. So there's a little bit, there's some little worksheets to go with this, so you can have an attempt at that and then look at the solutions on the accompanying video. Alright, I hope that is a bit useful. Take it easy.